Welcome everyone, my name is Romain and I'm happy to present you our replication study on synchronous transmission for Bluetooth 5 and IEEE 802.15.4. I would like to start this presentation with highlighting some of the keywords that are present in the title, and we'll start with the two technologies that we have been working with. As you may know, Bluetooth and 15.4 are two technologies that refer to the low power end of the spectrum. 15.4 is usually used rather for middle to long range communication, and it's quite reliable but rather low rate, whereas Bluetooth has emerged as a very pervasive technology, but so far mostly tailored to rather short range, high throughput communication. With the last release of the Bluetooth standard, Bluetooth 5, has introduced three additional communication modes. Two of them are lower rate, and that's due to the introduction of convolutional codes for forward error correction with different rates, thereby leading to two different bit rates. And the fourth rate of 2 megabits per second has been introduced by speeding up the symbol frequency outputting by the radio. Having all those different modes of operation is interesting because it really opens the design space of what can be done with the technology. And in particular, in this talk, I will talk about synchronous transmissions. What do we mean by this? Synchronous transmission is a technique that refers to the idea of letting multiple devices transmit messages at the same time. So typically, if we have the setting as shown on the right side, if A and B are both trying to send a packet to a receiver C, C will not successfully receive the message of either A or B because the two messages will interfere with each other. However, the idea of synchronous transmission and that may still work under certain conditions. There are two effects that are known to make synchronous transmission possible. They are known as the capture effect and the so-called constructive interference effect. The idea of the capture effect is that if one of the two transmitters, say A, has a stronger power, the signal has a stronger power than B at the receiver, then it is likely that C will receive the message coming from A if the time displacement between the two messages is smaller than the length of the preamble of the packet. The value of the threshold dependent on technology for 15.4 is known to be around 3 dB. The constructive interference effect, on the other hand, works only if both A and B sends the exact same packet, and it specifies that under time displacement between the two, which is small against the size or the length of a symbol, then it is likely to receive this packet at node C regardless of power threshold. This technique of synchronous transmission is extremely interesting because it has been shown to be a great building block for reliable and efficient flooding protocol. This was demonstrated about almost 10 years ago already with the Glossy protocol, and since then it has triggered a lot of work in this area. I will not cover any of those things, but if you're interested, a recent survey presents an overview of the state of the art on synchronous transmission-based protocols. Now, if there has been so many works done in synchronous transmission, why are we talking about a replication study? Well, last year, it was shown for the first time that apparently synchronous transmission also works on Bluetooth. So this is very interesting and promising because potentially we can transfer this 10 years of knowledge from 15.4 to the Bluetooth physical layer. However, it seems to be a bit more complex than what we were used to on 15.4, namely, success of synchronous transmission doesn't seem to be explainable only by either capture effect or constructive interference. And finally, so far, no one has confirmed that this indeed was working. So there's a genuine interest in seeing if indeed that works. So we have been trying to replicate those results. And as per the definition of ACM, the idea is that a different team should be able to replicate the results using a slightly different, even with a different system. So we have been trying to do this, and by doing so, we tackle essentially three different questions. The first two are related to the replication. First one is, does synchronous transmission work on Bluetooth? And if yes, can we explain it mainly with capture effect and constructive interference, as we were used to on 15.4, or is there something else at play? And the third question relates to benchmarking, which is the main theme of that workshop, whereby we wonder how to properly benchmark the performance of synchronous transmission. More particularly, what are the statistical methods we need to use in order to provide confidence in the results? So let's dive right in. Does synchronous transmission work on Bluetooth? As I mentioned, a replication study requires to use a slightly different setup than the original one from the authors. In the original study, the two transmitters were wired up using coaxial cables to the receiver. And so we've chosen to use a different approach where we take a different board, although having the exact same radio, and we do the experiment over wireless transmissions. We also put the entire setup within an anechoic chamber to avoid too much external interference. So you can see on the left side the picture of the actual setup. On the top left, you can see the two sides. On the left side, the receiver, and the right side, the transmitter, or the transmitters, I should say. Now, here are the results that were in the original study, or presented in the original study. You can see on the top graph the setting where the two transmitters send the same packet with roughly no time difference. And on the bottom, when they send different packets. So at the bottom, you can see the drops in the line that represent somehow the thresholds of the capture effect. And the difference between the top and between the bottom plot and the top plot shows the improvement that is gained when we send the same packet, and in particular when we have no time delta, so as shown on no power delta, sorry, as shown on the x-axis. You can see the reliability of the communication that still works thanks to constructive interference. Now we've reproduced the exact same experiment in our setup, and here's what we obtained. The graph look slightly different in the numerical number, but roughly speaking, the exact same trends are observable. So we conclude that indeed, yes, the results can be replicated. We use a different setup and we observe phenomena that are really, really comparable. Now, can we have a closer look and try to see whether indeed constructive interference and capture effect are sufficient to explain this success? And for that, I suggest we go and have a closer look at the entirety of the data we've collected. So here is the data visualization app that we have built within this project. You will find in there some information about how the data looks like, different panels showing different visualization. Here we're in the general exploration panel that will start with some filters or selectors for the type of data you want to look at, and some general visualization. I'd like to focus on the 3D plot where we see the PR on the vertical axis. On this axis here, the time delta between the two transmitters, and the power delta on the other axis down there. With all the data together on the plot, we cannot really see anything. So let's just look at one. The first thing we can see is that we have clearly this value here that corresponds to the capture effect threshold. We can see the threshold showing up here and there. Now, if I rotate on the other axis, if I look at the time delta, I can see that around time delta 0, I have the raising of the PR, which is characteristic from the constructive interference effect. So we do find and see the two things we are expected to find. However, there's one more thing I want to highlight here, that you can see that we don't get here at this plateau of 100% PR straightly at the same value everywhere. In particular, you can observe some kind of a triangle here that shows like when the time delta is small, I don't need that big of a power delta to reach perfect PR. That can be seen even better on other mode, for example. So if I put up the 125 kilobit per second mode, you can see that the thresholds, the values of the capture effect are not that straight, they are not that obvious. When we have no power delta, performance is bad, but as soon as I have a bit of power delta, performance increases, kind of regardless of the time delta. Now, more precisely, if we take a different slice in the slot, and we look at, for each of the Bluetooth mode, the packet reception rate against the time delta between the two transmitters. We see here the typical pattern of constructive interference where the PR rises when we get to a time displacement which is very close to 0, and then quickly flattens out as soon as we go over the size of one symbol. Now, at the other end of the spectrum, if we have a large power delta of about 10 dB, you can see that all over the place, the PR is at 100%. So here we are clearly in the constructive interference region, in the capture effect region, sorry. But now, in the middle, it's not black and white. In the middle, we have a progressive phase where the PR slightly but slowly increases and increases towards 100% more and more as the power delta increases, even though we are still not in the regime that it can be described as capture effect. So we call that this mixed region. We've been able to show this on Bluetooth modes, but also on 15.4. However, the difference in 15.4 is that this mixed region is much smaller, as the capture effect threshold is around 3 dB. Now, this observation is important and interesting because what it shows is that even a small power difference helps achieving useful packet reception ratio for small time differences that are already still larger than what is strictly required by constructive interference. So finally, So that's what we have observed. But how can we confidently claim that this is the case? What is the confidence we have in the results? Another way of saying this is, what is the probability to obtain the same results if someone else were to repeat our experiments? Obtaining the exact same results will never happen. So we can convert this question as, what is the degree of variation that is to be expected in the results? Now, if we take again the original study, the paper specifies that each experiment is run until at least 2,000 packets are being sent. So the only interpretation I can make is that each of those dots in this plot represent the data from run when we send 2,000 packets. With such data, the questions we have about the confidence on the result cannot be answered. Why? Because we did only the experiments once. So we don't have any clue, we don't have any information about the degree of variation that one is expected to observe. This is why we have used a different approach. And I show you the plot with only one mode for the purpose of illustration here. So what you can see is that each dot is the result of run, in which we run only 20 synchronous transmission attempts. So it's a much smaller number. However, we did multiple and independent repetition of those runs so that we can compute confidence intervals on the packet reception ratio that is expected to be obtained. So what you can see here with the colored area. And with such approach, we can answer the question on the degree of variation expected. We can actually claim that the median PRR for a set of runs will be between two values x and y, depending on the setting, and we can state this with a confidence level that is a probability of at least 75% in our case. If you want more information about this methodology and why and how it works, I will refer to another work of ours, which we call TriScale, that goes into all this in more detail. Now, coming back to our topic, once we have those reproducible measures of performance, we can use this to properly define the threshold for synchronous transmissions. For example, for the capture effect, we can set the threshold as the minimum power difference, such that the confidence interval is above, for example, 75%, regardless of the time delta. For the capture in the constructive interference, we set the threshold as being the time displacement under which the constructive interference, the confidence interval is above 0. With such definitions, we can define the threshold that we observe experimentally and compare them to the original study. We can observe that they are somehow in the same range, not exactly equal, but bear in mind that the original work did not formally specify the threshold they wanted to use, or how the threshold was defined, so it's difficult to compare. I want to conclude this talk with a few lessons learned we learned with this project. First and foremost, it was a great learning experience for us. Through this project, we learned a deep knowledge about the platform, and we actually have gained better understanding of synchronous transmission. And I think we can say that we are not amateurs in this area, and we still had a lot of things to learn. The second point I want to make is that the data must be made publicly available, because otherwise it's very, very difficult for others to try to replicate your work and most importantly to compare with it. For tons of reasons, things get lost, so saying that you will release things upon request is not really a viable option, so please don't do that. And finally, we have observed and we're convinced that data visualization is super important. It was really useful to be able to navigate all this data in all those different dimensions easily so that we can get more insight on where to go, when to have a look, where to dig deeper. But also, as a community, we must be more open to replication studies. And it's a great news for us is that this very workshop had as the first item of this call for paper, it was inviting precisely this type of work. And I have to say that in this context, it is really, really painful to see that half of the reviewers of our paper criticize the lack of novelty of this paper. This has to stop. And not all the papers are aimed to provide novel ideas. And so we need to get away from this sort of thinking. In particular in a workshop that explicitly welcome replication studies. So to conclude, we have indeed shown that, or confirmed, that synchronous transmission do work on Bluetooth as it does on 15.4. However, it does work in slightly different ways, and in particular, we have a quite big region of mixed effects between constructive interference and capture effect. I would like to encourage you to release your data, and if possible, also release the code for your data visualization. That will be useful for people that are interested in replicating your work. And I would like to encourage you to do replication studies yourself. It is very useful, it is good for science, and it makes a great entry into a topic for master thesis or first year PhD student, for example. I would like to point to 2 recent papers that were published in parallel to ours that go in more details into different aspects of synchronous transmission and different physical layers. Naturally, you will find all our data and our data visualization applications openly available online. Have a look and check it out.